This screencast is about some of the generalizations we can make concerning the types of ions that certain atoms will form when participating in ionic bonding. So from the last chapter, we know that the periodic table is organized into groups and that those groups are distinguished from one another by their physical properties. And what makes an atom act differently than another atom is the number of valence electrons, those electrons in the outer energy level. For certain atoms, it's going to be easier for them to lose an electron, and for other atoms, we're going to find that it's going to be easier for them to gain electrons, and atoms are going to do what is easier. So if we look at a sodium atom here with its 11 electrons, and when sodium becomes an ion, it's going to try and achieve the octet rule and have 8 electrons in its outer energy level. Right now it only has 1 valence electron. So it's going to lose this 1 electron and become sodium with a positive charge. That way it satisfies the octet rule by having 8 electrons now in its outer energy level, which just happens to be 1 energy level closer to the nucleus. We can do this for all of the elements in the periodic table. Now 3 through 12 in the transition metals, it is variable, and we'll discuss those separately. But here we know how many valence electrons they're going to have. We now have discovered that group 1 has 1 valence electron and is going to lose that 1 valence electron. Well, not only sodium is going to do that, but everything else. We're going to use the periodic table to help us with these generalizations. So we were just talking about sodium and how it likes to lose its 1 valence electron. Well, that is the case for everything in group 1. So for the most part, everything in group 1, when it forms an ion, it's going to form an ion with a 1 positive charge. I'd like for you to put 1 positive in that same spot on your periodic table. Group 2 has 2 valence electrons, and it's going to be easier for them to give up those 2 valence electrons to achieve the octet rule, much in the same way that sodium did. And so everything in group 2 is going to like to be at a 2 positive charge. Now, like I said, the transition metals, it gets a little interesting, and we'll talk about some of them. Now, we'll come and address those here in just a second. For the most part, those of the halogens, I'm going to start with the other extreme, have 7 valence electrons. When they become an ion, they are going to want to gain 1 electron to achieve the electron configuration of a noble gas. So when halogens become an ion, they like to be at 1 negative, gaining that 1 electron. Now, the noble gases have 8 electrons in their outer energy level. They do not want to gain or lose any, so they are not going to participate in ionic bonding. The oxygen family here, group 16, has 6 valence electrons. They need 2 electrons to complete their octet, so they're going to like to be at 2 negative. The nitrogen family, and really we're talking about nitrogen and phosphorus here, they're going to need to gain 3 electrons to complete their octet because they have 5 valence electrons, so they're going to like to be at 3 negative. Those elements in the carbon family, especially carbon and silicon, are going to participate in covalent bonding almost exclusively. Aluminum, even though it seems to be a metalloid, we generally agree that this is a metal, and when it becomes an ion, it likes to be at 3 positive. It has 3 valence electrons, and like all other metals, are going to give up those valence electrons and become a positive ion. Gallium will behave in much the same way. Zinc likes to be at a 2 positive charge, and so does cadmium. The other transition metal that we're going to discuss here, and I want you to add to your periodic table, is that of silver. When silver becomes an ion, it's going to lose 1 valence electron and just gain a positive charge. So now we'll be ready to write ionic formulas in our next session.